Hello everyone, today I want to talk about the Bohr atom, named after Niels Bohr, who came up with this model back in the 1920s. This is the model that has electrons residing in energy levels. Now you maybe talked about this in ninth grade, where you have electrons in level 1, level 2, level 3, level 4, and so on. And the periodic table is built up somewhat on this fact. Now why did Bohr actually come up with this model? What was he trying to explain? If I show you this picture, everyone would look at that and say, ah, a rainbow. All right, a rainbow, and it has all the different colors, Roy G. Biv of the rainbow. All right, now this is actually white light split up into the components. It was Isaac Newton that was the first to discover that white light actually is a blend of all the colors of the rainbow put together. So we've known about this phenomenon for a very long period of time. But in the early part of the 20th century, we had some spectrophotometric experiments that were kind of hard to explain. All right, what is this that we're looking at here? On the left, we have what's called a helium lamp. It's a lamp that contains the element helium. And if you look at that light through a spectroscope or a prism, you see only parts of the rainbow, not the entire rainbow. Now, what does one of these things look like? Let's pause for a moment. This is a neon light. It's a thin tube that contains the element neon, which is one of the elements on the periodic table. To make it light up, we put it into this high voltage power supply. And we have a neon light. Nice bright red light. Now we could take that long skinny tube and bend it into letters and shapes, and then we'd have a neon light that we could put in the window of a store or a restaurant or something like that. All right, it contains the element neon. That's why we call it a neon light. Now, if we put a different element in there, for example, this one contains helium, then we get a different color. So if you have different color neon lights, it's possible that it has something other than neon in it. However, there are neon lights that are just fluorescent light bulbs with certain kind of materials that give them different colors, but we still call them neon lights even though they really don't have anything to do with neon at all. Now, if we looked at this light through a spectroscope or a prism, then we would see the various colors that make it up. All right, and that's what this piece is here. So if we looked at this light right here through, we would see these various colors of the rainbow. Not the entire rainbow, but just little pieces of the rainbow. All right, so that's what that is right there. Helium light looking through a spectroscope. Now the spectroscope allows us to measure the wavelength of this light. For example, this bright yellow line right here in the middle is a piece of the rainbow. We only see in pieces of the rainbow, but this one here has a wavelength of, it looks like 575 nanometers, say. All right, nanometers, that's the unit we use to measure wavelength. Okay. Now, Bohr was actually trying to explain this kind of phenomenon. Why do we only see small slivers of light? His reasoning was this, that the electrons that reside in these energy levels possess a certain amount of energy. Level 1, level 2, level 3. As you go up, the amount of energy the electrons possess is greater. And electrons could jump from level to level. And they would have to either gain or lose energy in the process. So if an electron were to gain some energy, it could jump to a higher level. Say, for example, from level 1 up to level 2. Or from level 1, say, to level 3. And then the electron could jump back down. When the electron jumps back down, it will have to lose the energy it gained to get up there in the first place. And it might lose that energy in the form of light. And the electrons can only reside at the level, not somewhere in between. So there's a very distinct amount of energy that would be given off when an electron jumps from a high level to a low level. And that's why you only see slivers of the rainbow. Each one of these slivers of light represents a different wavelength of light, which can be measured with the spectroscope. For example, the bright yellow light right in the middle looks to be at about 575 nanometers. That's what those numbers represent. So each one of these colors represents a different jump from a high level back down to a lower level. And the amount of light, or the energy of the light given off, depends on how big that jump was. If you jump from a high level way down to like level 1, you'll give off a lot of energy. If you make a small jump, say from level 4 to level 3, you'll give off a lesser amount of energy and you'll get a different color. So each element then has a certain number of electrons and creates very distinctive jumps. And we sometimes call this an atomic fingerprint. And to see it, you would have to take the light given off by, say, a helium lamp and split it up using a spectroscope or a prism to be able to see the different colors. When all the colors blend together, then it's the color of the light that you see with your eye. All right, let's take a look at this model a little bit further. Now, what you learned probably in 9th grade is that each one of these energy levels can only hold a certain number of electrons. For example, level 1 can only hold 2 electrons, and then we say that it is full. So if an element has more than 2 electrons, you would have to put 2 in the first level and then move on to the next level, which can hold 8 electrons at most. Eight electrons. If an element has more than 10 electrons, then you would have to start putting them into level 3, which can only hold 18 electrons. And then level 4, 32, level 5, question mark, because we don't have elements that actually fill up level 5 at this point in time. All right, we could probably predict how many electrons would fit into level 5 if we had elements that completely filled it, but we don't really at this point in time. All right, now another weird thing kind of happens. Level 1, you fill it up with 2, but then level 2 can be filled with 8. When you get to level 3, you'll start filling that up until you get to 8 electrons, and then you'll not finish level 3, but start off level 2. And then you'll put a couple electrons in level 2 and then come back to finish filling off level 3 up to a max of 18. And then you'll move back to level 4. All this business is a little bit complicated, which we'll elaborate on a little bit more later. But the periodic table is actually laid out according to this pattern. Now, this number 8 plays kind of a significant role in the elements. This number 8, we call it an octet, which we'll learn about a little bit more later. All right, these 8 electrons that say fill up level 2 and so on are called valence electrons. And now, what is a valence electron? If we defined it, we simply could say electrons in the highest energy level. And these electrons play a special role when it comes to making bonds between atoms and forming compounds and chemical reactions and stuff like that. So these 8 valence electrons, which is the most that any element could have, play a significant role. All right, and we'll learn about what elements have these 8 valence electrons a little bit later. It happens to be the noble gases. All right, let's review how you might draw out a Bohr model atom on paper. All right, and you probably did this a little bit in 9th grade. All right, let's do a couple examples. Draw atomic diagrams for the element magnesium. Now, if we look at the periodic table, magnesium is number 12, meaning it has 12 protons and 12 electrons and some number of neutrons as well. To draw out these models, usually we'll start with the nucleus. And we could indicate that there's 12 protons and 12 neutrons in the nucleus of magnesium. And then we'll put some circles around it to indicate those energy levels, level 1, 2, and 3. And then we can draw dots on those circles to represent the electrons. So starting off with level 1, we'll put 2 dots. And it doesn't really matter exactly where you put them, but you kind of spread them out. And level 1 then is full. But we have to get up to 12 electrons. So now we'll move to level 2. And that can hold 8, so we'll put 8 electrons on level 2. And that gives us a total of 10, and we have to get up to 12. So now we'll move to level 3 and add the final 2 dots on level 3, and we're done. All right, we've got 12 electrons, and it shows electrons in 3 different energy levels, with only 2 in that highest level 3. And level 3 is not full either. Now, question. How many valence electrons does magnesium have? Now remember, valence electrons are electrons in the highest level, in this case, level 3. And how many of them are there? 2 of them. So we'd say that magnesium has 2 valence electrons, and they're in level 3. All right, let's draw another one. Potassium. On the periodic table, that's element number 19. All right, number 19. So we could draw that one out. Starting with the nucleus, we would put 19 protons and 20 neutrons, adding up to a mass number of 19. That would be the most common isotope. Now, how many energy levels do we need? Now, you maybe learned that these energy levels correspond to the rows on the periodic table. And potassium happens to be in row number 4. So we're going to need to have at least 4 energy levels to draw out potassium all the way. And we got to get up to 19 electrons. So we'll start with level 1, 2 of them. It's full. Level 2, 8 of them. It's full. That makes 10. And then we move on to level 3, and we're going to put in 8 of them. All right, now we haven't finished yet, but the weird thing that happens is that first we'll put in 8 in level 3, and then we're going to jump to level 4 to finish things off, even though 3 is not filled yet, because 3 can hold 18. We're going to jump to level 4, and we're going to put 1 electron, and now we have 19. All right, we have 19, 1 electron. And this is significant because potassium happens to be in the first column, and anything in the first column has 1 valence electron. Anything in column 2, where magnesium was, will have 2 valence electrons. So potassium has 1 valence electrons. Level 3 is not completely filled, and we only have 1 electron in level 4 for potassium. All right, now it does get a little bit more complicated than this, but we shall take that bit up a little bit more later, and then we'll see how the periodic table is laid out also according to this business. All right, next we should do a lab to look at atomic spectra and the colors that light makes when electrons jump from level to level.